All right, so welcome everybody for the CERIAS seminar series, and the talk today that I'm going to mention is differential guarantees for the cryptographic systems. My name is Aniket Kate. I'm an assistant professor here at Purdue. Okay. So we use cryptography in quite a lot of different scenarios, and I'll say that almost all of us have started to use now cryptography in some form or other. Uh, Typical things that are getting used in cryptography even in our day-to-day life is encryption. Most of our most of our communication that we do with our banks or just even our email communication is now end-to-end encrypted between the server and your local machines. We use them for the signature to ensure the authenticity, that you're talking to right server and that you're getting the right messages and not people are not changing your message on the way. And then there are also interesting other things such as commitments and zero knowledge proof that are also started to get used in various other interesting scenarios. So as I already mentioned, SSL TLS is certainly the most prominent form of the cryptographic mechanism that we use and on the regular basis. And so is the case with the password authentication or SSH that also most of you as a students must be using for your conversation. Some of you might be using even fancier tools such as PGP to make sure that your messages are signed, or maybe Tor if you want to achieve some kind of anonymity, or maybe some of you might be encrypting your MacBooks where you're using file vault, or maybe there are some e-voting mechanisms that you use. So, and I'll certainly make a claim that we are going to see more and more use of cryptography, and even now we are doing that, and we'll be doing even more of that in the future to come. So when we talk about cryptography or when we talk about the security, the first thing that we need to talk about in the notion that is of interest to is the privacy here. And when we talk about privacy, the first person that we have to consider is the adversary. Who is the adversary? What is the threat model against which we are working in? And the key thing there is again that adversaries come in different form and shape when we talk about its come on internet. As I'm showing here, it can be just a friendly neighbor who is trying to snoop on what you're doing, up to the state level programs which are trying to find out information at the mass level. So there are adversaries that can come at a different level. And then in most systems, to actually quantify this adversary, we try to introduce the concept of auxiliary information. So by auxiliary information, I mean that information that adversaries can obtain about your communication, about what you're trying to do, how are you trying to do, when are you trying to do, from some other medium. Okay, so auxiliary information can be just some information that they know. It can be some metadata, as we remember, which is basically how, when, who is sending, and without knowing what's the data. So there is all sort of this auxiliary information. And therefore, what we try to do is that given that adversary can be very strong and can have access to a lot of auxiliary information, we go for a really strong notion of security. Rather than we just say that adversary should not be able to know some information for the message, we just say that he should not be not able to any even single bit of information regarding your message or regarding your encrypted communication. And that's where the concept comes, which is known as indistinguishability. So what I mean by indistinguishability, that I thought I'll just show that with a more diagram form. Okay, so the typical way we define indistinguishability is we'll assume that there are two machines, machine x0 and x1, okay, which represent your algorithm, your protocol that is performing, and there is an adversary. Okay, and we'll assume that this adversary interact with one of these two machines chosen uniformly at random. Okay, one of the two machines. And it will look at these through this interaction, it will try to determine whether it is interacting with machine 0 or machine 1. Okay, and then the idea is that when we say we have perfect indistinguishability, the best possible privacy, if adversary cannot distinguish between the two events, whether it is interacting with machine 0 or whether it is interacting with machine 1. Okay. Very simple way to consider that how these machines are related to cryptography. Let's say basic encryption as a mechanism. So machine 1 will be using the exact same algorithm, but it will be encrypting message M0 or maybe just message 0 bit. Okay, while machine 1 will be something again using the same algorithm but encrypting the message 1, and that's one way to distinguish between the two messages. Okay, in principle we also assume that adversary is the one who picked these two machines and given. So typical for when we talk about the privacy guarantee, what we want is that adversary, although he provided the two machines, eventually when one of them is picked, uniformly at random, then he cannot distinguish which of the two is getting used. All right, and the perfect indistinguishability, which typically we achieve with one-time pad, if you have already done some study in there, is happens via when we say that the probability that adversary interacting with, let's say, machine x0 and obtaining and providing an output, let's say that it's actually interacting with as if giving output 1, which means it's interacting with machine 1, is equal to the probability that it outputs that the same value 1 when it is interacting with the machine x1. Okay? But in many situations we cannot achieve this perfect guarantee, and what we settle with is known as a computational indistinguishability, where we say that instead of these two probability being equal, we say that they are actually almost equal and bounded by a small factor, which typically we know as delta, and this delta factor is negligibly small, very small, okay, exponentially small in the situation which is associated with the security parameter. So we define a security parameter, and we expect that value to be in these two probabilities to be not too far from each other and bounded by this small value delta. Okay. So this computational guarantee allows us to define various different cryptographic primitives for starting from our standard encryption, public key encryption, or in many other scenarios like commitment and many other protocols. Now moving slightly away from the cryptography, and now we talk about a interesting problem regarding privacy, which is the privacy preserving data analysis. Okay, and the examples there are just lots of examples that we have to deal with of such things in our real world. For example, there are databases of health records, census data, web analytics, and in all these scenarios, the statistical information from this database is collected and published online. Okay, and obviously this statistical information may provide some kind of information regarding individual entries in these databases. And when we try to actually achieve the privacy preserving data analysis, what we want to achieve is that although these statistics are released, this information is released, at the same time we still try to protect the privacy for the data for the entries which are present in this particular database. And the question that we ask is that now this is again a basic privacy problem, and can we use the same rigorous definitions like indistinguishability that we studied earlier to this data privacy problem? And answer turns out to be no, and we'll just understand what's happening in this respect. The first thing that we'll have to understand here is that what do you mean by privacy in this data analysis scenario, these data release scenarios or statistical information release scenario. Okay, and even in the database literature, even before we define cryptography formally in 1977, Delineus actually provided the definition which has really good meaning, good semantic guarantees. So what we say that anything that can be learned of an individual from a statistical database can also be learned by the adversary without having access to this database, this statistical information. So something you already know about this particular individual or this particular entry, okay, or this particular individual without using the statistical information, then statistical information should not increase your information regarding this individual. Okay, this guarantee, for example, here just to understand, my adversary will be somebody who is querier. So he is the one who is going to make the query, obtain the statistical information, and now use this information to find out more about an individual. Okay, an example that I'm going on the next slide should make it more clear. The one thing that we have to understand why this is analogous to what we saw already in the indistinguishability, right? So in the cryptographic scenario, we know this indistinguishability that I mentioned is known to be equivalent in several scenarios to what is known as semantic security. So semantic security is a notion which says that anything that can be learned from the that can be learned from an encrypted message. Okay, let's say you encrypt a message and you know any information about that message by looking at the ciphertext can also be learned even without having access to the ciphertext. Okay, so let's say you know that the message is either yes or no. That information, that auxiliary information that you already have about the message. Now you get an encryption of this message. It should not increase your information that you can obtain. with, regarding whether it is yes or no. So that's what we call as the semantic security. Okay, and this is the notion which is equivalent to the indistinguishability that we saw earlier, and basically this the notion that is provided the delineates for the database release or release of the statistical information for the database has the equivalence to this notion. Now, if just putting this in slightly different perspective, let's say what we are comparing this scenario is basically an adversary, which is an algorithm, and auxiliary information, and we're comparing that with the same adversary and with this auxiliary information and some statistical information regarding database, and we're comparing this. And what we want to say that the prior and the posterior view or the information that adversary can get of about an individual should not change much. So basically we are comparing the left hand side and the right hand side, and there should not be a huge difference in the information that adversary can obtain. Okay, but the key question that we want to ask is how much is too much, right? I mean, it should not know too much information. In the most ideal scenario, we want this information to be negligibly small, so that then which is very which closely equivalent to the standard cryptographic setting. But as it turns out, that won't be the scenario in database release, because this information is closely related to the amount of that the statistical information should also provide some utility or some help, so that you can understand or obtain some information from this answer to the query. So the key thing is that the mechanism that achieves cryptographic level of small negligible advantage to the adversary possibly cannot provide the useful information to the as the answer to the query. So just to give an example, as it turns out, we can actually prove this impossibility, that we cannot achieve the best the cryptographic privacy guarantees and some kind of utility from the database, and that can be shown by this very simple example. Okay, let's say I'm taking a contemporary example, and my example, let's say Russia knows as an auxiliary information that Donald Trump is 0.5 inches taller than an average US person. Okay, and therefore let's say somehow we find out, we do a computation and we obtain the average height of a US individual, adding this answer that we obtain from the statistical answer that we obtain from the database, and adding the information that Donald Trump is 0.5 inches taller, we immediately know the answer or the height of Donald Trump. Okay, so this example just shows the difference between, in the sense that what can be learned once we add this auxiliary information, which is basically difference between the height of Donald Trump and the average US person. And this will immediately leads to the leaking the privacy for Donald Trump. Okay, so that just shows that indeed it's a given the auxiliary information can immediately break into the privacy, and for any individual or any such using in our case basically the example that we take, the Donald Trump. Okay, the key interesting thing to remember see here is that this works even when the Donald Trump is not present in this database. Okay, let's say we are talking of that, let's say the Donald Trump is 1 inch taller than an average person, let's say from UK, and now in this database he won't be present, and still we will be able to use this auxiliary information and this answer that we get from the statistical query to obtain information regarding him, or rather break his privacy. Okay, so that shows that there is certainly this auxiliary information that can play the role. So that motivated, however, an interesting definition, where that what if we consider different privacy notion, where basically we'll compare the two privacy leakage, whether basically we compare the leakage, what if the particular entry or individual is present in the database or whether they are not present in the database. And instead, for our notion, what we are going to do is we compare these two notions, that probability that answer will be a particular value such that that particular entry is present in the database, and probability of that will compare with the now the same database, but now this individual included, and we'll compare these two probabilities, and if that difference is not significant, then maybe we can actually make some meaningful guarantees regarding the privacy, because now looking at the output we cannot be sure whether this particular individual is present in the database or not. And that leads to the concept of differential privacy, which would basically means that these are the privatized or differential privatized database, so that the output for such database remain indistinguishable whether a particular person or whether a particular entry is present in the database or not present in the database. So, let me try to show that with a example here. Okay, as I am showing, typical as with the standard cryptographic systems, it is a game between adversary and a challenger. Okay, my challenge is on my left hand side and my adversary is on the right hand side. Okay, and what happens typically, as with our earlier example, an adversary is going to pick two database or two tables which differ in, let us say, one row, and he is going to send these pick these two tables and send them to the challenger. Now, what challenger is going to do is that pick one of them, okay, and run the algorithm, their algorithm to obtain the answers on top of that. Okay, typically it will be randomized algorithm, and obtain a result, and now send this result back to the adversary. Now, an adversary who has access to this answer should not be able to determine, okay, whether the table, the blue table is chosen or the green table is chosen, which is just a single bit of indistinct information that it is not aware of. Okay, and that is what the challenge that it has. However, the key thing to remember is that instead here, not only we will have a delta factor which provides a distinction at the additive layer, but on top of that, in the differential privacy, we will also have a multiplicative factor, which I am showing there with e raised to epsilon, okay, such that which will add a quality to this distinguishing, so that an adversary providing a correct output, an adversary which is providing an incorrect output, they are not, when we compare them with each other, they will be actually related with this equation, where the left hand side is less than or equal to e to the epsilon, which is the multiplicative factor, multiplied with the the right hand side probability with a small delta factor over there. So, it is interesting, this makes us ask, what does this multiplicative factor mean? Okay. So, this is an interesting concept on itself, because if these are the probabilities that we are comparing, and now we are saying that for simplicity I am assume that this delta factor is 0. Okay. That we typically expect that to be negligible, but maybe assume that is 0. And when we are comparing these two probabilities, we are saying that the two probabilities are now associated with each other by this multiplicative factor, which indicates that there is, although one probability where the adversary guessing correctly can be higher, but it will be always bounded by a factor which is closely related to the second probability where he is going wrong. In principle, it means that he can never be sure, because of this multiplicative factor, he can never be sure that let us say what he has guessed is the correct answer. There is some kind of a deniability which is always available to the challenger, saying that no, you are wrong with this particular probability, which is bounded and provided by this e to the epsilon factor. So, basically when we talk about differential privacy, one way to interpret that is that it provides you a deniability that indeed what is output by the adversary is incorrect, and that deniability is determined by this epsilon factor. So, that is typically the way it is used, and maybe I will say the differential privacy provides us the guarantees where rather than just completely giving up that there is any kind of privacy hope which is possible when we talk about the privacy preserving data analysis. Instead, we at least get a way to achieve some kind of a privacy guarantee even in that scenario by introducing this multiplicative factor. Okay. Now, indeed, an interesting question can be, is this data privacy database or data mining privacy or data release privacy is the only example where we can have a differential privacy kind of guarantee, or are there some other scenarios where it can be also helpful and where we can use such a deniability notion to get some kind of a meaningful guarantee rather than just giving up upon the hope to achieve some kind of a privacy. And as it turns out, this talk we are going to see two interesting examples where we are able to achieve the similar guarantees in the scenarios outside the data privacy scenario. Okay. Instead of, there is also an interesting way to put it, is that where can we use or abuse the differential privacy notion in suburb scenario, and we are going to see two prominent examples from my earlier work, where initially we use, in the first example we use that for the cryptographic protocol with imperfect randomness, where we are able to employ the similar concept to achieve some privacy guarantee, where otherwise we could not provide any privacy guarantee in the standard notion. And the second example that we are going to see is the anonymous, the privacy property for the anonymous communication networks such as Tor, where we are again able to use the similar guarantees to achieve some kind of a privacy which otherwise was not possible. So let me start with the randomness example. I guess those of you who already taken some kind of a crypto lecture or even security lecture, you know that to get good privacy guarantees, typically most cryptographic algorithms use some kind of a randomness. Okay, that we certainly need that, because when we talk about the secret key, that secret key should have some entropy, and the best way to do that is that secret key should be chosen uniformly at random or with some randomness guarantee. Okay, and most primitives are also randomized, and that's also required for notions such as the semantic security, indistinguishability. So given that, we use randomness quite a lot in all the cryptographic solutions, or for that matter in most security systems. Okay, the examples of encryption, commitment, zero knowledge proofs, secret sharing are all these scenarios we required such randomness. In most scenarios, even if you heard me already, what we expect this randomness to be is uniform. Okay, so such that it's an interval which goes from some, let's say, value 0 to some n, and one of these values is picked uniformly at random. Okay, so that each of them has a probability to get picked which is uniform. It's 1 divided by n, basically. That's what's going to happen in this case. Just to give an example how typically this happens, I consider very simple primitive, which is a commitment protocol. So a commitment protocol, it's a protocol between a prover and a verifier, and it works in two phases. In the first phase, the commit phase, the prover actually wants to commit to a particular message, okay, or a particular information. So he takes this message and the randomness value r, and basically it commits, use a commitment algorithm to take this message and the random value r and obtain a commitment c. And now this commitment is sent to the verifier or Alice, and the requirement that we have, the privacy requirement that we have, is that seeing this message, this commitment c, the verifier should not have any information regarding the committed value m. Okay, that's a guarantee that we want. And then what happens in the latter phase, in the reveal phase, the Bob will reveal the value of the message m that it has committed to and the randomness that is employed, and now verifier can take these information and basically check whether this committed value c is actually associated with the message m and the randomness r. Okay. So and the key, and second property that we want typically from the commitment scheme is binding property, where it should not be possible for this prover to change the message afterwards. So once you commit to something, you have to reveal only the same message m and not something else. Okay, and as you can see here, when we talk about for our discussion, we will be focusing on the privacy property, and that we can just explain with this simple example, where we'll assume that, let's say, our adversary, which will be the verifier over here, is going to pick the messages. So Alice here picked two messages, green message and the blue message. Okay, send those two messages to the prover Bob. Okay, and Bob, now what it does is it picks one of these two messages, it tosses the coin and picks one of these message uniformly at random, and then picks a randomness from a uniformly random source and commit to these things to obtain this black box as I'm showing there. And the black box or the commitment value is sent back to the verifier or verifier, who is Alice here, and which will be also our adversary in the privacy game. And now we compare the two probabilities as with the previous case. We'll compare the probability that, let's say, the blue value is committed to. Okay, so I'm talking about now the thing on the left hand side, where I'm saying that the blue value is committed in this black box, and I'm saying that the probability that adversary is going to claim that the value is going to claim that indeed the blue value is what it is committed to. And I'm comparing now the same output, black, and I'm saying that let's say now instead we have committed to the green value, and now adversary is still claiming that the blue value is the one which is committed to. So, on the left hand side we have something which where adversary is correct and the right hand side adversary is wrong, and we are comparing these two probabilities, and we say that this probability should be bounded. Okay? And the key thing that we want is that this value here should be this delta value there in this equation should be negligible, so that he cannot find out which of the two value is committed to, okay, whether it is a green value or whether it is a blue value. Okay. And that's the thing that we wanted. But the key thing that I want you to focus on in this particular example is this source of randomness. So, for this protocol to work correctly in most scenarios, we need an access to the uniform random source, so that this value r that is used for the commitment is the uniform is chosen with a uniform random source or from a uniform random source. However, if you go into the real world, access to the uniform random source is a very difficult thing. Most of the things that we deal with in the physical world have some kind of a causal relation. So one thing is related to other thing. So maybe most of the source that we employ for obtaining uniform random may not be random enough. Okay, so real sources are not perfect random sources, are not uniform random sources, but they are somehow imperfect sources. And the interesting question to ask that, let's say we replace this ideal uniform random source with this imperfect source, can we still achieve the guarantees that we want? Okay, and that's we'll call as a concept of tolerating the imperfect sources. So we'll replace the randomness source that we employed, and we replace the uniform source in the ideal scenario with a non-uniform source, and still we ask the question, is the protocol still remain secure or not? So the one thing that typically happens is that rather than doing that, in most there's already significant literature in theory which comes under the term of randomness extractor, where given such a non-uniform source, we basically apply an algorithm on top of that, so that we can convert that source to a uniform source and now use that. Okay, so the idea typically is that maybe rather than when you want, let's say, k bits of uniform randomness, you extract k plus some x number of bits which are not uniformly random but almost perfect, and you will basically have an algorithm which given this k plus x bit to convert them to k bits, so that those k bits are uniformly random. Yes?
So are you saying with the difficulty of getting perfect randomness, you would have two different random generators and you'd switch between the two to provide the differential privacy you're talking about?
So currently I'm just talking about a source, and that source is not perfect. It's not uniformly random, but instead it is imperfect. It has some, as we are going to see later, it will have some minimum entropy or something like that. And I want to start from this one source and then apply an algorithm on top of that, so that to convert that to a uniform source with maybe fewer bits. So I'll start with more bits and convert them to fewer uniform bits. That's what I'm going for. Okay, it's possible for some sources, but there are some well-studied sources in theory at least, such as Santa Vazirani source, for example, is one example, or there can be also block sources which are known as, where we know that we cannot always convert them. Given such a source, some k bits, we cannot convert them to uniform random source, except if you are willing to give up, if you are willing to go for the exponential blow up. What I mean by exponential blow up is that, let's say I want k bit of uniform information, okay, or uniform randomness, and it's always possible that you are given 2 raised to k bits of imperfect source. You can convert them to the k bit of information. But let's say I don't want to do that. I want to do that maybe only polynomial number, take polynomial number of inputs and convert them to the some kind of uniform source. There are several examples which are known in the literature where you can't do that. Okay, exponential blow up is certainly something that we can't take care in most practical scenario. Okay, for example, if you want 128 bits, you cannot expect to have access to 2 raised to 128 bit of large, so it's just impossible to store even that piece of information. So the well-known example for that is indeed this Santa Vazirani sources, and which are basically biased information. So basically, it's an example of it's a generalization of bias coin. So I mean, the equation is there, but just to give the idea, in this case, basically you are going to keep on drawing an individual bit from such a source, and the next bit that you're going to draw will always conditionally based on all the previous bits that you have drawn. Okay, that conditionality is defined by this parameter rho that I'm showing there. Okay, and basically the idea is why this source makes sense in the physical. Let's say we use some physical source for measurements, and in that to obtain our randomness, then typically the bit that we draw can be historically related to all the previous bits that are drawn from such a source. So given that, given if we are provided such a biased source where the new bit that we draw depends upon all the previous history, in such scenario we cannot take such a source and convert that to a uniform random source, okay, except with the exponential reduction. Now, given such SV source, people have already started to study their effect on the cryptographic system. Let's say we replace our standard uniform sources that we require for cryptography by such non-reducible, non-extractable sources such as Santa Vazirani sources. So if we take the authentication or the signature primitives or message authentication codes, the primitives which require authenticity but not privacy guarantees, there, as it turns out, we can use this SV source and get almost equivalent guarantees as uniform source. So as I'm showing that in capsule, the Santa Vazirani sources are on the green part. That means we can use them for our cryptographic protocols or for our cryptographic implementation and still get the guarantees that we want. However, when we want privacy guarantee, when we want indistinguishability kind of guarantee, as it turns out, these SV sources, there are impossibility results which have shown that there is a probability that given any SV source, I will be able to find out a protocol or a situation where we cannot achieve the indistinguishability notion that we want for our messages. Okay, and it has been shown first time one-time pad, and later in a stock 2004 paper by Dodis et al. It was shown that the same hold for encryption, zero knowledge proof, commitment, secret sharing, all these primitives. Basically, anywhere you have indistinguishability guarantee, we cannot use this SV source. And the reason they thought about it is because they went for this standard cryptographic indistinguishability guarantee. So just to demonstrate what I mean by that is that let's take this example regarding commitment, and we expect that our adversary Alice, the verifier, provided 2 messages. Now the Bob, the prover, actually commit to one of these 2 messages, okay, and the key thing it uses, the randomness that is used by the Bob is actually some Santa Vazirani source, let's say, which is a biased randomness, and then this black committed output is provided back to the verifier. Then we cannot ensure that there can be scenarios where the adversary can tell apart which of the 2 messages committed to by looking at this output and performing some conversation. Okay, and especially we are talking about the secure protocols here. That means if we replace this non-uniform source by a good uniform randomness or a perfect randomness source, then this protocol could have been actually proven secure. Okay, so we are talking about in this scenario where the randomness result into the lack of privacy. The question that we ask is that maybe, but this is happening only because we are considering for the indistinguishability kind of a notion. What if we are more than happy to actually settle on a slightly weaker notion which is similar to differential privacy, and we can overcome this thing? And that's the question that we ask. I mean, is it all lost, or it's not that all is not lost? Can we replace this perfect or the computational indistinguishability definition that we use for the commitment and replace more like a differential privacy kind of a notion and still obtain some kind of a meaningful guarantee? Okay, and the answer that we obtained from our the first result is indeed that's the situation. So in what we basically show is that as I'm showing in 2 examples, on the top I'm showing our standard definition that we saw earlier. Let's say it's a game between a challenger and an adversary, where adversary has to determine whether it is communicating with machine 0 or machine 1 x0 or x1 as I'm showing there. And in the top scenario, it's this challenger is provided a source which is uniformly at random. Okay, and on the we say that in that case, if adversary gets a standard indistinguishability kind of guarantee, where when we are comparing these two probabilities, the probability that adversary is right with the probability that adversary is wrong, they are actually both close to each other by a negligible factor delta. Okay. And now what I'm doing in the things below on the second part is basically replacing this uniform source by a non-uniform source, okay, by a source such as Santavadiriani source. And in that case, what we do is that just with this difference, instead of saying that now there is no privacy, we give a bound on the privacy where these two probabilities are not only now related by this delta factor, but instead they are also related by a multiplicative term which we represent that as in an exponential form like e to the epsilon. This can be also write as a 2 raised to epsilon, it does not matter that much. And in principle, I am also changing delta to the delta prime because we add a small factor which get added to this delta. But however, if the initial value was negligible, this delta prime also remains negligible. In principle, what we obtain is that if we have delta indistinguishability with the uniform source, then we obtain actually e comma e raised to delta e raised to epsilon delta differential indistinguishability for a source which is basically in let's say a particular Santavadiriani source. Okay. And not only that, we can provide also relationship between the parameter for Santavadiriani source as well as epsilon, and they are basically related to each other with a constant factor. Okay. So the interesting thing to us is that we know how to go from one way to other. Given an example which works in the standard uniform setting, we know how to convert that to the differential indistinguishability setting. We use a different notion. We don't just wanted to use differential privacy as a term because it has its own meaning in the database privacy community. So instead, that's the reason we use the term differential indistinguishability to show the relationship of this to the cryptographic things. And the interesting question to ask that we can go from the top to the bottom. We can go from the uniform source to the non-uniform source. But can we always go from the differential indistinguishability kind of a notion to the indistinguishability notion? And the answer is no. Answer is actually no. The counter direction does not always hold. Okay. And the idea is that there can be scenarios where we get the differential indistinguishability, but we cannot convert that back to something which is indistinguishability in perfect sense. Okay. And a delta indistinguishability, as I mentioned. And obviously, the differential privacy is a common example for that, where in the database scenario where we know that we just cannot achieve, even when we have access to the uniform source or whatever, we cannot achieve a indistinguishability kind of a guarantee, and we have already settled on there in something like differential privacy. So what is the application of that to something like commitments? Okay, so most prominent example for commitments are electronic voting protocols. Okay, that's why they are used quite a lot. And then the idea is that I voted on something, and my privacy depends upon that the commitment cannot be open. Okay. In the traditional setting, we'll just say if my source, randomness source that I use on my laptop, my phone was not random enough, then don't expect any privacy. But instead, now we say that rather than don't expect any privacy, you say that you will always have access to some kind of this epsilon delta kind of a differential indistinguishability, which is much better than saying that you have no privacy. Okay. So we say that there are actually interesting privacy which can be defined, and like with the differential privacy scenario, it will be deniability kind of scenario. So adversary may have more hunch that probably you voted to A than to B in the voting scenario, but you can always have deniability that no, there is a probability that adversary think it's A, but there is always some probability which exists with which you could have voted participant B. Okay. And we can provide this guarantee with this epsilon delta notion for the indistinguishability, which otherwise was not possible with the standard indistinguishability notion. So that's just one way to interpret. There are more interesting things that can happen based on the cryptographic application. What kind of interpretation we can perform, we can obtain given this epsilon and delta value, and that's a certainly interesting thing to explore further. All right, so now moving on, I want to give my in last couple of slides, I want to give another example where we found this notion to be interesting and useful, and that example is anonymous communication networks. Okay, so Tor is the most common scenario where we try to use anonymity. By anonymity here, I mean that you are actually sending some message to a server, and you want to protect from, let's say, your ISP or some servers on the internet whom you are communicating with. Okay, and in some scenario you also want to protect that the server or the website that you're visiting to, that website should not know what is your IP address. Okay, and in standard anonymous communication scenario, the way we achieve that is we pick some of the proxies, some of the routers on the internet. Okay, in system like Tor, these are the nodes which are freely available, and that you can obtain information regarding that from a available server, and you pick some of these nodes, typically 3 nodes that you pick, and you send your communication through this 3 nodes so that it's encrypted. It looks different in the different part of the network, and you use this path to actually communicate with the server that you want to communicate with on the internet. So as I'm showing here, basically in the figure, you can see that the messages looks different in the different part of the network, and because it looks, let's say, greenish on the first part, and then with a different color in between, and so on until it reaches the server. And this is done with the encryption mechanisms, and then as long as an adversary cannot see all these message paths and how they are flowing, he cannot determine which user is talking to which server. Okay, so that's the way typically Tor provides some kind of anonymity. That's like one very basic description of how it happens. Okay, but we still don't know very well what is by anonymity here. Okay, we know this is we want to achieve, but quantifying this anonymity, similar to as we have done with the cryptographic primitive, has been an open problem or challenge for several years. So what we did as our first effort is to actually try to quantify this privacy or the anonymity that we obtained from such anonymous communication network. And as we realized that we can't just pick one notion and try to achieve all these properties. Instead, we require multiple notions such as sender and receiver anonymity, relationship anonymity, unlinkability, to actually quantify or define these different guarantees that we achieve. Okay, this information depends upon what is your adversary. I mean, just to clarify, if my adversary is my ISP and not the end server that I'm going, then I want a receiver privacy in the sense that the ISP should not know which server I am visiting to. If my adversary is the final destination server where I want to visit it, let's say I want to go to google.com, but it should not know my IP address because they can track me, then in that case I'm going for the sender anonymity, such that the receiver or the last node should not have any idea who is the sender for a particular message. Okay, so what we did is we defined these guarantees and then try to actually measure them in interesting scenario. So the first thing that we want to do is the modeling this anonymous communication, and the key thing that will be required there is the anonymous communication. We have 3 key messages. Okay, the sender of the message, the receiver of the message, and the message itself. Okay, typically for the simplicity of the analysis, we assume that the messages are something which are common across the different scenarios. They will not become the key hurdle for defining the privacy notion, and that will become clear soon. And now, given such a scenario, the idea will be we'll take such a table as an input, and we'll run this sender, receiver, and message table through the anonymous communication network. And an adversary will be somebody who will have access to the some links and the some nodes in the system, and it should not be able to actually get some kind of privacy notion the way we define it. Okay, so another way to now look at this is that this now I define similar to how I define differential privacy. So adversaries will have two tables which are adjacent, which are close to each other in some form or other. How they are adjacent to each other, I'll define very soon. Now they are given to the challenger. Challenger take these two tables, which are basically sender, receiver, and message, and send them through the anonymous communication channel. An adversary will see whatever it can see at the nodes that are under its control. And now looking at this information, it should be able to determine which of the two tables are chosen by the challenger. Okay? And as it turns out, we observe that even here we have the guarantees which is very similar, that we compare an adversary determining that it has chosen correct table. I mean, on left hand side, the blue table is chosen, or the blue set of senders and receivers is chosen, and adversary determines that it's actually blue, and we compare that with the second scenario where the green one was chosen and adversary still says it's blue, and we say that they are now related with the epsilon delta in a very similar way as we defined earlier. Now just to make it clear what I mean by the adjacent table here, so let me take the simplest example, which is sender anonymity. Okay? In the sender anonymity, what we want is we want the privacy or the anonymity for the sender. So the way I define it in the most basic form is I am going to take two tables chosen by the adversary. They are same except in one place, except in one location where the sender will be different. Okay? So for example, in the table that are shown here, on the first two entries are exactly the same in both scenarios. Okay? In the both tables, they only differ in the sender, which changes from the Alice to Bob when we go from the table 1 to table 2. Okay? So in the blue table, the sender is Alice for the third message, and in the green table, the sender is Bob. Okay? As you can see, all other entries are exactly the same in both scenarios. Okay? I'm also keeping the same receiver in both scenarios, that you can see there. So receiver is the same. Only thing that change, only single bit of information that change is that the sender changes from Alice to Bob. Okay? And we say that we feed in these two tables to this system. Challenger picks one of them and execute, and an adversary should be able to determine whether the blue table is chosen or the green table is chosen. Okay? So given these two things, the idea is to compare, and we still want to make sure that the adversary cannot distinguish between these two scenarios. Okay? The way we define this thing typically is we call this alpha adjacency, because what may happen that these tables which are provided by the adversary may require some more fine tuning. So that in the most typical scenario, what happens is there are two tables which are provided by the adversary. They go through this this alpha adjacency mechanism, which depend upon the sender anonymity or receiver anonymity or unlinkability or relationship anonymity, do the further processing on these two tables, and then they are sent to the challenger, and the challenger then basically execute or picks one of these two tables and perform the operations, such that now looking at the information that is flowing through the network, adversary should not be able to determine which of the two is chosen. Okay? In the sender anonymity case that we saw, basically this adjacency algorithm doesn't need to do more. Okay? But in the more complex anonymity notions, he has to do the processing, and that's the reason we introduced that over here. But the question that still remains to is that why we have this requirement of multiplicative factor or this epsilon factor. Why can't only we do with the standard delta notion? And to make it understand, let me just give an example kind of why we see this multiplicative factor here. Okay? Let's say typically an adversary has an auxiliary information that there are two users, Alice and Bob. Okay? And let's say Bob prefers green nodes. Let's say green node shows US, and let's say pink node shows they are nodes from Europe. Okay? And the idea is that typically Bob prefers the nodes in US for its communication, while Alice prefers the nodes in Europe, and that's typically happen in many of these node selection strategy, that maybe for the efficiency purpose, you assume that let's say Bob is in US, so he's going to pick the nodes in US so that his communication will flow fast, while Alice on the other hand is in Europe, so she'll pick the nodes which are go through Europe, so that her communication remains fast. Okay? And let's say adversary has this access to information, but adversary doesn't know which of two have sent the message. But let's say uh, it sees now a message that is flowing through, let's say, pink node. Okay, and adversary has access to one pink node and one green node, and it sees that the pink node that is under adversary communication see a message going through it. Then, based on the chances that the Bob is, let's say, going to pick the green node versus pink node, given this probability, there will be high chance that when it sees when it sees the message going through a pink node, typically it's going from Alice. Okay, and given this guarantee, there will be adversary will know that with higher probability the message is coming from Alice, but not from Bob. But it can never be sure, because typically in all these scenarios we have a probability that, let's say, 75% of chance that Bob is always going to pick the nodes in the green side, but there is a 25% chance that Bob is also going to pick some of the pink nodes. And let's say I'm going to put the similar probability for Alice, who is going to pick the pink nodes with 75% chance, and with 25% chance she is going to pick the green nodes. Now, given this guarantee, adversary will, once you see a message on a pink node, it's know that most probably it's coming from Alice, but there is still always some probability that's coming from Bob. And given such a probabilistic guarantee of the picking nodes, which is employed in most of this node selecting or path selecting strategy, as it says in onion routing literature, there remains some deniability which is available to the Alice and Bob in our example, so that they can always deny that they actually they are not the one who has sent this message. And this deniability property is exactly capturable in the multiplicative factor, as we saw earlier. And indeed, that provides another example for us where we can actually employ this this multiplicative factor, this differential kind of a guarantee, to achieve some kind of a privacy notion. Okay, so as I mentioned, this these events, although an adversary sees that the message is flowing through a pink node, is not always a distinguishing event. Okay, but it still has some information, and this information is captured by the differential guarantee, which provides us another information. So those are the two examples that I wanted to give, and with that I'm going to end my talk, giving that indeed I'll say not always there are scenarios where we cannot obtain the best possible guarantee for the privacy, which is indistinguishability, but we may have to settle on something weaker in terms of the differential guarantees. And there are scenarios naturally existing where we can obtain such guarantees. This study started in the form of differential privacy for database release, but in this talk I showed two examples, one in the cryptography itself and the second for the anonymous communication, where indeed we obtain similar guarantees naturally. Okay, thanks a lot.